Hey everyone, thanks for taking the time to tune into my presentation. My name is Mohammed and I'm currently a postdoc at the Center for Water Resources at Dalhousie University. I'd like to acknowledge my co-authors, Dr. Victor Bense from Wageningen University in the Netherlands, and Drs. Barrett Kurlick, Rob Jameson, and Julia Gimon from Dalhousie University. Today I'll be talking about a couple projects we've been working on that involve the development and application of numerical models capable of simulating reactive solute transport in cold region groundwater systems. So as my title suggests, most of my talk is going to revolve around the effects of freeze-thaw and permafrost processes on groundwater flow and solute transport. This figure on the left shows the distribution of permafrost in the northern hemisphere, which shows that it covers roughly 25% of the terrestrial land surface, and more importantly, most of it is in some state of thaw due to warming associated with climate change. Northern latitudes are currently warming at more than double the global average rate, and this is expected to at least continue, if not intensify, in the next few decades. The distribution of permafrost has a strong influence on the hydrologic functioning of northern landscapes, as it affects the partitioning of snowmelt into different components of the hydrological cycle, as well as has a significant impact on the connectivity of different surface and subsurface water reservoirs throughout the landscape. Throughout the Arctic, there is increasing evidence of changes to the hydrological cycle, particularly in wintertime and snowmelt-driven processes. This figure on the upper right shows increasing baseflow trends across northern rivers in Canada. An unseen process underpinning these various hydrological changes in cold regions is the thawing of permafrost, increases in active layer thicknesses, and increases in groundwater flow, and reactivation of previously dormant groundwater systems brought on by warming temperatures and thawing permafrost. An important question for many reasons is what effects will climate change have on different types of permafrost environments? And how will this affect the future hydrological, biogeochemical, and ecological processes in the cryosphere? The thawing of ice-rich permafrost in the north is already having a number of ecosystem changes to northern landscapes. In some areas, the settling and collapse of the ground surface converts dry lands to wetlands. In other areas, the loss of frozen ground promotes more vegetation growth, and this causes a transitional greening of the environment or landscape. Perhaps more importantly, thawing of permafrost has the potential to release the vast amounts of carbon currently stored as frozen organic matter in soils and sediments throughout the Arctic. Permafrost thaw can also have significant implications for engineering infrastructure in northern communities and industries. The settling and consolidation of the ground can also damage infrastructure like pipelines, storage tanks, and geosynthetic liners at waste management facilities. These obviously pose a risk of releasing various contaminants into the environment. A recent example is the oil spill in the Arctic caused by a leak to a fuel tank, which authorities said was damaged due to permafrost thaw. Increased development and these increased risk of contamination events coupled with increased hydrologic connectivity due to permafrost loss means that we can probably expect a higher risk of groundwater contamination in northern environments in the future. So with northern environments transitioning to a more active groundwater flow regime, there is an urgent need to develop methods and tools to improve our understanding of and ability to predict how these climate-driven and anthropogenic events will affect the movement and storage of various reactive chemical species in the subsurface, be it associated with the mobilization of nutrients released by permafrost thaw or with subsurface contamination in a permafrost setting. The major difference in groundwater flow and solute transport processes in cold regions compared to warmer climates is of course the influence of permafrost and frozen ground processes, whose dynamics are governed by the surface and subsurface energy transfer processes throughout the landscape. Numerical models of groundwater flow and solute transport are commonplace in hydrogeology and are considered an integral part of any groundwater investigation. Most groundwater models, however, generally do not simulate both freeze-thaw processes and reactive transport, and moreover, most models do not consider the coupling of mass and energy transport processes and associated effects like temperature-dependent chemical reactions or the effects of elevated solute concentrations on the freezing point of groundwater. So we took a stab at developing such a model. We used the generic numerical model FlexPDE, which is a well-documented code used to simulate groundwater flow and permafrost dynamics. And what we did was we modified the code to accommodate groundwater flow and solute transport in addition to energy transfer with freeze-thaw, which is needed to simulate both reactive transport and permafrost processes. We use well-established partial differential equations describing mass and energy transport, which, don't worry, I won't show here. Most of our efforts were spent on developing the constitutive relations or the physical relationships, describing things like the effects of solutes on ground freezing characteristics and the influence of temperature on solute reaction properties. So I'm going to show some results from a couple of preliminary applications of the model to investigate some scenarios where groundwater facilitated solute transport may be important in permafrost landscapes. The first is a modeling study done in conjunction with the government of the Northwest Territories to investigate the potential of contamination associated with a wastewater lagoon located in the boreal zone of discontinuous permafrost. And the second study investigates the mobilization and transport of dissolved organic carbon released by permafrost thaw. For our first study, we investigated the potential for contaminant migration associated with groundwater flow from a small wastewater lagoon in the Northwest Territories, which is used by a small community of about 100 people. There were a few monitoring wells at the site, and from that we had access to some geologic information, as well as some information on groundwater flow and water quality in the vicinity of the lagoon, as well as the lagoon itself. We combined this data with nearby meteorological data and information on the site topography to develop a groundwater model of the site. We were unsure about the extent of permafrost at the site, so we used this available data to develop a few different models of permafrost scenarios to see if there was any risk of contaminants from the lagoon impacting the nearby river in the area. So this slide shows the approach we used to develop a groundwater model for this site. As permafrost distribution and active layer depths are governed by ground surface temperatures, estimates of those ground surface temperatures are needed to provide upper thermal boundary conditions for our groundwater model. Ground surface temperatures are determined by the surface energy balance of heat fluxes due to radiation, turbulent fluxes of sensible and latent heat, and ground conduction heat fluxes. To account for these factors, the surface energy balance of the site was first simulated. We used the surface energy balance model to estimate the expected ground temperatures and active layer depths and permafrost distributions at the site. This information was then used to prescribe thermal boundary conditions for the groundwater model. So all partial differential equations need initial and boundary conditions, and this figure shows the model domain and the various initial and boundary conditions we used in our study. Because we're simulating three transport processes, groundwater flow, heat transfer, and solute transport, the initial and boundary conditions for all three transport equations were needed to drive the model. Based on the site weather data and energy balance modeling, we started with a stable permafrost condition as our base case scenario, and then ran the model for 50 years under stable and warming climate scenarios. Initial concentrations for the different contaminants simulated were based on water quality samples taken from the lagoon and monitoring wells. So this figure shows solute concentrations in the immediate vicinity of the lagoon at the end of a 50-year simulation period with stable permafrost and seasonal active layer freeze thaw for three different contaminants, a conservative solute like chloride, and then two reactive contaminants, nitrogen and phosphorus. The conservative plume extends to 11 meters below the surface of the domain. However, the bulk of the mass is within the upper 5 meters. The plume spreads horizontally about 15 meters, and this is because the groundwater flow in the area is not that fast during active layer seasons. For the reactive contaminant nitrogen, the plume is far less persistent due to the combined degradation as well as the temporary immobilization from seasonal freezing in the active layer. Because of those slow groundwater fluxes, the degradation rate rivals the advective flux of the contaminant, resulting in minimal horizontal migration of the reactive contaminant nitrogen in these simulations. The phosphorus plume is also much less persistent than the conservative solute, as most of that mass is adsorbed during the active layer transport. Both nitrogen and phosphorus plumes range in depths from 2 to 3 meters below the base of the lagoon, coinciding with the base of the active layer. We also ran a similar scenario, but in this case, we looked at the effect of elevated solute concentrations on pore water freezing. Experimental evidence has shown that soluble salts, like chloride, can decrease the freezing temperature of pore water by increasing the osmotic potential of the solution within the soil. The net effect of this phenomenon is to increase the amount of liquid water present at sub-zero or freezing temperatures. The reduction in liquid water content in the soil as temperatures fall and ice forms It's described using a relationship called the soil freezing characteristic or soil freezing curve, where this W parameter shown here in the upper right is related to the temperature transition window over which liquid water decreases and ice forms. So we developed a concentration-dependent soil freezing curve, which increases the temperature window of that water-ice transition period, or the mushy zone of the SFC, shown in this purple region, when chloride concentrations were over a certain threshold in the model. And you can see in the lower right here that in the vicinity of the lagoon, elevated salt concentrations cause the permafrost to have higher water contents and thus higher permeability. Simulations for this scenario with the modified soil freezing curve show that elevated salt concentrations can potentially have an important effect on contaminant migration. All plumes show enhanced migration relative to their corresponding simulations with the unmodified SFC. In particular, the conservative salt and phosphorus plumes show significant increases in mass at depth due to solute-induced thaw, which increases the effective permeability of the permafrost and allows for further migration of solutes. The nitrogen plume, however, does not show an increase in mass as the degradation rate is still higher than the advective fluxes. These results show that when solutes allow more liquid water to be present at freezing temperatures in permafrost, transport may be enhanced due to the increased permeability of the permafrost. However, the minimal contaminant migration in these results, along with those from the previous scenario, suggest that permafrost, if present and stable, can be an effective barrier to contaminant migration from the lagoon. So like I said earlier, permafrost is known to be degrading in the region. So we also ran some simulations with permafrost subject to surface warming so that permafrost thaw continuously occurs. This simulation shows that, as expected, permafrost thaw allows for enhanced migration of solutes compared to stable permafrost. At the end of a 100-year simulation period shown here, the plume is pooled at the top of the thawing permafrost, and horizontally the plume is spread about 200 meters. The solute mass from the lagoon never reaches the river in this simulation, however. We also ran some simulations without any permafrost, which are not shown here for the sake of time, but all simulations show a relatively low risk of any contamination from the lagoon reaching the river, and most degradable solutes are naturally attenuated before reaching the river. So the results from this study and the simulations here suggest that groundwater in the immediate vicinity of the lagoon may be impacted, especially if permafrost is thawing. These results are consistent with field monitoring results, but overall the lagoon poses a relatively low risk to the river. For my second study, we look at the effects of permafrost thaw and increased groundwater circulation on the mobilization of sequestered carbon that can be released by permafrost thaw. This figure shows the various pathways by which all carbon stored in permafrost, that is, carbon frozen as organic matter, can be mobilized and transported and released into the environment. As permafrost thaws, vast stores of old carbon currently stored in permafrost are susceptible to potential mobilization and degradation to greenhouse gases, generating a positive climate change feedback. Most research focuses on this vertical release of carbon from these stores to the atmosphere, but a portion of this carbon from thawing permafrost can be laterally transported by groundwater to surface waters by groundwater discharge. This lateral carbon flux via groundwater discharge to surface water is potentially comparable to the Arctic's regional capacity to absorb anthropogenic CO2. Thus, an improved understanding of the effects of groundwater flow on carbon mobilization is crucial for predicting changes to the Arctic and thus global carbon cycling regime. So in this study, like I said earlier, we focused on these deeper stores or pools of old carbon, which were generally stable and not part of the active carbon cycle until recently. But with climate warming and permafrost thaw, part of this carbon will be leached into groundwater, increasing the contribution of old permafrost carbon to DOC export. So simulations were performed on a generic permafrost hill slope domain to better understand the biogeochemical consequences of permafrost thaw. This figure shows the domain, initial and boundary conditions employed in this study. We also simulated groundwater age or residence time to see if we could tease out any relationships between groundwater residence time and carbon export. In this scenario, the solute reservoir simulated represents a pool of previously stable, old organic carbon that becomes leached into groundwater as dissolved organic carbon. Simulations examined the carbon reservoir initially encased and unreactive in permafrost. Models were subject to long-term warming trends, and results were analyzed to quantify changes in groundwater flow and carbon export brought on by permafrost thaw. So I want to stress that this is still a work in progress, and we're working on fine-tuning our parameters to better match reality, but we're able to see some really interesting results so far. Model simulations so far agree with field observations that indicate continued permafrost thaw and increased groundwater discharge will result in substantial increases in the fraction of old carbon export, but that the total amount of export can be mediated due to different biogeochemical conditions in the subsurface, as well as the bioavailability and lability of that organic matter. So we can have a range of possible DOC export scenarios, which is not new news, I'm fully aware of. But all scenarios show a period of what we call peak carbon, which is essentially a period in the simulation where the largest fluxes of carbon export occur. And this period seems to be related to the complete loss of permafrost in the hill slope and the reactivation of the full groundwater cycle, and thus periods of increased groundwater discharge. So I'm just going to show a video from one of our simulations, which shows that permafrost is gradually thawing from the top down, which allows dissolved organic carbon to be produced from this thawed organic matter. As permafrost continues to thaw and groundwater flow system becomes more developed, we see DOC concentrations reach a maximum and then stabilize. So again, this is still a work in progress, but we think models like this will be helpful in better understanding the future possible changes to Arctic hydrological and carbon cycles. So we still have quite a lot of work ahead of us, but we think we have some encouraging results. The preliminary modeling suggests that wastewater lagoons may be a viable waste management option for other similar small communities in the north. We plan to collect some more field data when we can travel safely again, and to investigate site-specific factors such as topography, soil properties, distance to surface water systems, climate, and permafrost conditions. We're also planning on applying our carbon model to some real data to see how it holds up. So just to conclude, we think that building reactive solute transport processes into groundwater models can improve our ability to understand the fundamental processes that ultimately dictate the flow and storage of nutrients, heavy metals, and possible contaminants in cold environments. So that brings my talk to an end, and I'd like to thank you all for taking the time to listen to my presentation. I would like to thank Amy Jackson and Lindsay Johnston for assisting with data processing. And finally, I'd like to thank the government of the Northwest Territories and their partners who funded this work. Thanks again for listening.